Any questions about anything? Last time or anything? Well, today we're starting a new chapter, and finally we're getting into something that feels a lot like calculus. We had to discover basic fundamental properties of the real numbers, like the least upper bound property, because it's going to make the things we did in freshman calculus legitimate. And so it's going to feel like we're going back to freshman calculus, but we're going back and looking at it again, thinking about it more deeply and understanding when it works and when it doesn't work. So finally we're going to start talking about sequences, and we're going to start using the word limit. You kind of felt like maybe soups and imps had a lot to do with limits, because we were always taking sequences that snuck past various boundaries to demonstrate facts about them. And in fact, the least upper bound principle meant that when we tried to take a limit to get the square root of 2, we actually got something that was the square root of 2. So it was kind of in the background. We weren't saying the word, but it was there. But we've been seeing the sequence 1 over n a lot, and so that's the one I'm going to use to motivate sequences. So the formal definition of a sequence would be a map. So a sequence would be a map phi from the natural numbers into the reals, and we would write the x sub n would be phi of n. Okay, and the notation of the book, the book writes a sequence in multiple ways. Let's see, sometimes they use a capital X. That would be they use a capital X to denote a sequence of numbers xn. My personal favorite way to do a sequence is to write x sub n, n goes from 1 to infinity. That's my favorite, although the book doesn't do it that way. And let's see, you could say x sub n such that n is in n. Anyway, they all mean the same thing. And when the book wants to write as little as possible, it uses a capital X to denote a sequence. I wrote something above. I wrote x sub n. Let's say x sub n tends to a limit, L, as n goes to infinity. This is the same as writing the limit as n goes to infinity of x sub n equals L. And I got to tell you what we mean by that notation here. So the definition of that notation. In freshman calculus, you used words like, oh, x sub n gets arbitrarily close to L as n gets big. Kind of fuzzy language like that. And in the book, you had to read the famous epsilon definition of limit, but they didn't sort of force you to think in those terms. It's actually important to think in those terms, otherwise you could make mistakes. So the formal, it took lots of years for mathematicians to come up with the right way of saying what a limit is. They had to make some mistakes on the way and think about it pretty hard. Anyway, the definition that turned out to be the right way to think about it is, suppose we have a real number r. So later on we'll talk about the case of a limit being plus infinity or minus infinity. But that's not, we're not thinking about anything that fancy yet. L, the limit, needs to be a real number. And then we'll say the limit as n goes to infinity of a sequence x sub n equals L. That's going to mean, given any old epsilon bigger than 0, no matter how small, I like to add that. That's not in the book. No matter, so A, it has to be positive, but it could be really small. There is a positive integer n such that the distance from xn to L, so that's the absolute value of xn minus L, is less than epsilon when little n is bigger than or equal to capital N. That's the correct way to say what a limit is. By the way, the book uses a greater than or equal to n there. Some books just say greater than an n. So greater than n gives the same definition. And some books say greater than instead of greater than or equal to n. Doesn't matter. Let's see. So the way you ought to think about this definition is that epsilon stands for an error or a tolerance. So think epsilon is the error that you might get in a measurement. Or if you're an engineer, you might think tolerance. How precise do I have to make my parameters so I get my thing within some tolerance of L? That one's more for engineers. Okay, and I guess I'd like to draw some pictures here. Here's one way to think about it. I always think graphically. So here's a big long real line, and I'll have here the integers 0, 1, 2, 3. Getting tired of this, but 5, dot, dot, dot. Capital N, the one in definition, capital N plus 1, capital N plus 2, etc. Okay, and here's my limit, L. I'll draw a horizontal line like that. And then epsilon, L plus epsilon would be a little bit above that L, if epsilon is small. So here's my L plus epsilon. And here's my L minus epsilon. Well, the thing that says, the definition says eventually those x sub n's get stuck in that band, that narrow band. And so starting with n, the x sub n's are stuck in here. Maybe I'll make them purple. So it would get stuck in here. That's x sub n. The next one I graph might be below. Every now and then you might actually hit the limit. But from this point on, those things are stuck in that narrow band. Before you get to, there's no 0. What? Oh, that's really a bummer. My 1 is kind of bigger than it should be. The early ones before that could go all over the place. So they could be above there, they could be negative, they could be way above there. They could go inside. They could actually hit L if they wanted to, but usually they're all over the place maybe. But eventually, you get a tail end of the sequence that's stuck. So I like to, people call this the tail end of the sequence. And the book is going to use that sort of as a scientific term. The tail end of the sequence. The tail end of the sequence eventually gets captured in that narrow band. And no matter how small that narrow band is, you can always find me an N, such that that's the case. Okay, that's one way to draw a picture to understand it. There's other ways to think about. To say that xn minus the limit is less than epsilon when n is bigger than or equal to n. By the way, the book likes to write n of epsilon. That means the n depends on epsilon. And I don't do that because I'll let the book write all those epsilons. But it's important to realize that if I shrunk my epsilon more, then I might have to go farther out to the tail to make this picture happen. So the n depends on the epsilon. So other ways to say this when n is bigger than or equal to n. Let's see, a common way. We've seen this interval, this neighborhood, epsilon neighborhood interval. So that was notation for the x such that x minus L is less than epsilon. So one way to say that, let's see, that's the epsilon neighborhood of L. So here's L, and here's L minus epsilon, and L plus epsilon. And it's an open interval because it's strictly less than. And so that, that set is this shaded region here. That's the V sub epsilon of L. Okay, so one way to say it is that x sub n is in this epsilon neighborhood of L when n is bigger than or equal to n. And of course, or you could say that L minus epsilon is less than xn is less than L plus epsilon when n is bigger than or equal to n. They're all the same. Well, the classic example I mentioned at the beginning is x sub n equals 1 over n. And if I want to show that goes to 0, then I want to, it goes to 0 as n goes to infinity. Because, give me any epsilon. Then we would have xn minus the limit less than epsilon. In this case, that would mean 1 over n minus 0 is less than epsilon. And of course, that's absolute value of 1 over n is 1 over n. And if I invert both sides, that would change the direction of the inequality because they're positive. So this would be n bigger than 1 over epsilon. And this is the aha moment. Archimedes' principle says there's an n that does that. exclamation point. That's why Archimedes was thinking about it. So there exists such an n. Let's let capital N be the first one. Let capital N be the first n such that n is bigger than 1 over epsilon. Then, if my n is bigger than or equal to capital N, then we can go backwards in these inequalities. Then n is bigger than 1 over epsilon, and we can follow those inequalities backwards. So follow, and they would be valid. So follow the string of inequalities. I'm going to be careful the first couple times I do this, but then I'm going to get casual with this little thing because it's going to be the same every time. Follow the string of inequalities back upwards. Making sure each one is true. Get that 1 over n minus 0 is less than epsilon when n is bigger than n. Okay, so that form, it's not hard to see that this limit exists. Well, now there's going to be some exercises in this section that feel a lot like freshman calculus. So another example, the same string of inequalities, string shows, even if I had a thing that changed signs, minus 1 to the n, so that flip-flops between plus 1 and minus 1 divided by n. I could put that in that same string of inequalities, and that would also go to 0 as n goes to infinity. And in fact, I could put minus 1 to the n sine of n over n goes to 0 as n goes to infinity. And that's because the sine function is always between minus 1 and plus 1. So I'll say, why is that true? And so when I do the estimates like I did above, let's see, the absolute value of minus 1 to the n sine of n, that would be the absolute value of sine of n, and that would be less than or equal to 1 because the sine function wiggles up and down between plus 1 and minus 1. Question?
If we can show that the limit of something is L,
Yeah.
and we can show that that thing is, say, always bigger than L, does that mean that L is the infinum?
Yes, that would be a true thing. And in fact, that's how eventually we're going to use the least upper bound principle and the greatest upper bound principle to show that limits, the things we do with limits are legitimate. Okay, so, by the way, this sequence sine of n is really a wild sequence. You can always find a subsequence that converges to anything between 0 and 1. So it's kind of like going all over the place. It never settles down anywhere. It's not like plus and minus 1 to the n, which flip-flops back and forth between plus and minus 1. The sine of n thing just goes all over the place and never settles on anything. And the reason is, like sine of n pi is 0. And so it's since pi is irrational, sine of n pi let's see, sine is irrational. So pi, you can find rational numbers that are close to pi. And then you think, okay, p over q is close to pi, so p is close to q pi. And sine of q pi is 0. So you would hope that sine of p is would be close to 0. Anyway, it's a wild and crazy thing. It's bounded by 1, so that's all I care about in this example. But it's a fun sequence to think about in the future. Questions about anything so far? Okay, so I'm going to start feeling like a little bit like freshman calculus here for a minute. Let's see if we can figure out what 5n plus 2 over 2n plus 7 converges to. Or it gets, if it converges, and what if it does, what to what. Well, the trick you learned in freshman calculus is when n is big, I can multiply by 1 over n. The biggest power of n in each numerator and denominator is n to the 1. And if it was n cubed, I'd divide by 1 over n cubed. But it's n to the 1, so I'm going to divide top and the bottom by 1 over n. So I multiplied by 1 in that form. And that would be 5 plus 2 over n, which I think is something really small. And on the bottom would be 2 plus 7 over n. Also something small. So we guess that this is going to go to, so at the moment I'm just guessing, this is going to go to 5/2 as n goes to infinity. And in freshman calculus, you were allowed to think like that. But now I'm going to do the let epsilon be bigger than 0 thing and demonstrate that my guess is correct. Then let's see, I have 5n plus 2 over 2n plus 7 minus 5/2. I want that to be less than epsilon. Well, now I'm going to mess around with this thing and cross multiply and get 2 times 5n plus 2 minus 5 times 2n plus 7 over 2 times 2n plus 7 I want that to be less than epsilon. A lot of stuff cancels on the top, and I get, there's no n's up there. I get 4 minus 35. That's minus 31 over 2 times 2n plus 7. Absolute value. And I want that to be less than epsilon. So I'm going to stop writing want. Okay, well this side is 31/2. This is positive. So this is 31/2 over 2n plus 7. I want that less than epsilon. And now I see what I need. Let's see. These are both positive things. So when I take 1 over it, I get 2n plus 7 needs to be greater than 2/31, what? 31 over 2 epsilon. I'm thinking of epsilon as small o, so that could be a gigantic number. But then you see what I need here. I divide by half and subtract 7/2. I need n bigger than 31/4 for epsilon minus 7/2. And so I let capital N be the first one that's bigger. Bigger than that. So that's how you would do it using the definition. And we're going to demonstrate facts that would mean we don't have to go back to the definition every stupid time we do this. But some of them are kind of fun. Let's think about this. Questions about that? We saw this example earlier in the semester when you had to do a math induction. I mentioned it in Piazza. This is a famous example from freshman calculus. Square root of n plus 1 is slightly bigger than the square root of n. And in fact, as n goes to infinity, these get really close together. And these go to 0 as n goes to infinity. And it's a classic example that you did in freshman calculus because this looks like this one's going to infinity, this one's going to infinity, and so this looks like it should be infinity minus infinity. Which, okay, you might say that's, okay, infinity minus infinity, it's got to be 0. But in freshman calculus, that's an indeterminate case. I could make it turn out to be anything. I could get something big minus something big, which converges to infinity. I could make that first something big a really big thing, so that when I subtract even something that's a little bit big, it goes to infinity. I could also make it go to minus infinity, or I could make it go to any real value. So in freshman calculus, we harp on the fact that this is an indeterminate form. You got to be careful and think about it. And in this particular case, here's how we think about it. So we have square root of n plus 1. This is kind of a trick. There's the thing I want to analyze. I'm going to multiply by 1. And let's see, the idea is to make the thing in the numerator a difference of squares. It's kind of like rationalizing the denominator, stuff like that you learned how to do in junior high. So, big idea, I want to make the thing on the top, numerator, be a difference of squares. So I'm going to multiply by 1 in the form of that. So I didn't change the value by doing that. But on the top then, I would get square root of n plus 1 squared minus square root of n squared over the denominator. And of course that thing on the top is n plus 1 minus n. Which is 1. And so this thing that looks like it might, who knows what it goes to, is actually obviously really small. Okay, and having two things in the denominator, that is the thing in the denominator is even bigger than the square root of n. So this would be even less than 1 over the square root of n. Okay, now I'm going to do my epsilon thing. I want to show this is going to 0. So I want this to be less than epsilon. Then I would go backwards and see that my original thing is less than epsilon. Okay, so then you just go through and think, okay, I can square both sides and get 1 over the square root of n squared needs to be less than epsilon squared. And of course, that's 1 over n. And then it's the same as the first example I did, the simplest thing. So I need n to be greater than 1 over epsilon squared. So take capital N to be the first one, first such n. Archimedes' principle says there is such a thing. Questions about that? Yeah.
Look at 1 over square root
How did I get that? Let's see. Um, let's see. Square root of n plus 1 plus the square root of n is bigger than the square root of n. So when I do 1 over it, it's less. Good that you asked that. Okay, so now lately I've been showing you examples that actually converge. When you want to show that something doesn't converge, you would have to come up with epsilon for which this thing fails, just so that xn doesn't converge. You have to come up with just one stupid epsilon that doesn't work. Just one epsilon where this game fails. The book actually uses the word game. This is kind of a game. Okay, so the classic example is the alternating sequence between +1 and -1. Let's see, x to the n equals -1 to the n. That alternates between being +1 and -1. So if I were to graph it, here's +1, here's -1, 1, 2, 3. It starts out at -1, and then it's +1, and then it's -1, and then it's +1, and then it's -1, etc. And so, of course, those aren't getting squished into a narrow band. And it's pretty easy to show that those don't converge to anything. Let's see, what should I take my epsilon to be? If I take epsilon less than, let's take epsilon to be a half. Okay, and then we would see that we would need -1 to the n minus a limit to be less than a half. Okay, when n is odd, that would be L minus 1. What? And when n is even, that would be L plus 1. Well, those sets are just joint. And so, of course, you can't make both of them happen. So if you think about it, here's 1, here's -1, here's 1, and these sets are disjoint. So there's no such L. And then when you think of that picture, I could let that epsilon half get bigger and bigger until those two intervals touched each other. And so you could see that epsilon equal 1 also fails. And anything less than 1 would work, but anything bigger than 1, well, then you run into the difficulty that those sets intersect. So there are some L's that satisfy both those things. Okay, so that thing doesn't converge. Interesting, when we'll talk about subsequences, I could take a subsequence that's all +1 all the way. That one converges. And I can take a subsequence that's -1 all the way. That one converges. So it'll be an interesting question sometimes whether or not that's a possible thing to do. Your book today does some interesting things that I want to make it easier for you to read. Let's see. Let me do another example. This is a really important example. If I have a real number between 0 and 1, then powers of it go to 0. Okay. And you learned this in freshman calculus, and the easiest, most transparent way to study it is, let's see, so we want to show that we want r to n to be less than epsilon. The easiest way is to use the log function. Okay, so I'm going to graph the natural log function here. The natural log of 1 is 0. Okay, this is the graph of the natural log of x. It shoots down to -infinity at 0. But it's a strictly increasing function. That's because its derivative is 1 over x, and that's strictly positive. Okay, so let's think. This r to the n, r is between 0 and 1, so r to the n would be between 0 and 1. So when epsilon is 1 or more, we're done. If epsilon is bigger than or equal to 1, all the r to the n's are less than epsilon. So we only have to think about epsilons that are between 0 and 1. If epsilon is between 0 and 1, then it's over here. And I want my r to the n to be less than epsilon. And the fact that this is a strictly increasing thing means that r to the n minus epsilon, r to the n is less than epsilon if and only if the log of r to the n is less than the log of epsilon. That's because that thing is a strictly increasing function. Okay? So it's because of that. Okay, that's something you need to sit down and convince yourself that you believe. Okay, so and this thing, remember from freshman calculus, the log of r to the n is n log r. Okay. Well, the natural log, and see the graph in the picture, if something's less than 1, the natural log is a negative number. So this log of r is between 0 and 1. This is a strictly negative number. And the log of epsilon is between 0 and 1. So it's also a strictly negative number. So I'm going to take minus of that inequality and get minus n log r is greater than minus n log epsilon. Okay, I took minus that inequality, but now the good news is that this is n times minus log r. This side is minus log epsilon. These are positive numbers now. And so I see I need n to be bigger than minus log epsilon divided by minus log r, which is a positive number. And of course that's equal to log epsilon over log r. But those are negative numbers. Okay, so I take my capital N to be the first one. And then I can go backwards and get the inequality I want. So that shows that r to the n goes to 0. Questions about that? There's some other famous limits that are mentioned in this section that I'll do here. Other famous limits. Useful also. So a famous one is if you have a number that's positive, then the limit of the nth root of a positive number, you learned this in freshman calculus, so you'd remember it under hypnosis probably, tends to 1. And if you started messing around with your calculator taking root after root, you would believe that. And one of my favorites is the limit as n goes to infinity of n to the 1 over n is even 1. Let's see. Okay, so it's cheating at this moment to take logs and exponentials. But I did it anyway. Cheating to take logs and exponentials. Because I haven't really studied them in detail yet in the way that we're doing math analysis from first principles. So cheating to use logs and but the book shows that it can do something clever and avoid using logs and exponentials to deduce these facts. And I don't want to get too bogged down in it. So the book cleverly uses Bernoulli's inequality, which is something from the section on math induction, really, Bernoulli's inequality, namely, if x is bigger than minus 1, then 1 plus x to the nth power is greater than or equal to 1 plus nx for all n. Okay, that's a very clever math induction. I guess it's not too clever. It uses the binomial theorem. So in math induction, and the book does it on page 30. It uses the binomial theorem in elementary math induction. And it's not hard. You ought to look at it as an example of a great math induction. Okay, so the book uses this Bernoulli's inequality to demonstrate these things. And of course, it's a little bit technical. So it uses Bernoulli's inequality to prove the above facts. But let's think about cheating. I'd rather cheat. Let's cheat. Oh, I'm going to take, what is n to the 1 over n? N to the 1 over n is e to the log of n to the 1 over n. And that's e to the 1 over n log n. And 1 over n log n is a famous thing. It looks like 0 times minus infinity. It's one of those indeterminate forms. And so 1 over n log n, I'll write it again like this, is log n over n. And you use L'Hopital's rule. To show that that goes to the derivative of, so let's see, this tends to, so that's not an equal. That tends to the limit as n goes to infinity of the derivatives, d by dn of log n over d by dn of n. By the way, we're going to demonstrate L'Hopital's rule from first principles later in this semester. So that's why I'm cheating. And of course, that's the limit of n as n goes to infinity of 1 over n. And that's 0. And the exponential function is continuous at 0. And so this thing is going to tend to e to the 0 equals 1. Because of that calculation and the fact that e to the x is a continuous function. Words that we don't know yet. So it's okay to think in those terms, but when you have to demonstrate something, you have to play by the rules that are in the section. I can get away with cheating at the end of class here. Question?
Since we are always will use the L'Hopital's rule to the...
No, you're never allowed to use that until I say so.
But for here, you use L'Hopital's rule to prove the 1 over n times log n is goes to 0.
Right.
You can just directly prove 1 over n